Hi, so today I'm going to be discussing what a pull-up resistor is and how you can use a pull-up resistor to create a data line. A lot of the descriptions on the internet on how this works, they're closer to simple than those nonsensical explanations of what a transistor does by far, but it's still just a little bit confusing until you have some practical know-how and until you actually see what it does and how it does it. So when do we need a data line inside of a laptop? Let's say we have a battery and we have a system management controller that reads the battery. So you know when it tells you what the percentage is that's left in the battery, that is the battery communicating with the computer. And it's going to do that on a data line. How do we create that data line? We create that data line with a pull-up resistor. So here's what I mean when I say I'm creating a data line with a pull-up resistor. A lot of people think that you're simply creating a data line by just shooting data out, and that's it. Well, in some circuits, the way it works is you have a circuit that will actually create data by taking an existing signal and simply pulsing it down and bringing it down to ground every now and then. Think of it like Morse code, where every single time you tap that little thing, it creates a little beeping every time you tap it. Except here, every time you tap on that little Morse code thing, every time you hit it, you're actually removing a signal instead of inserting a signal. So let me just show you what I mean with some pictures and practical application, because this is not going to make a damn bit of sense to you until you actually see it. So here is the SMC. Here is the battery charger chip, and here is the actual battery. Now these all talk on these data lines. So you have one line over here, SMB BSA CLK, which is clock. And then you have SMB BSA data, which is the data line. So you have a data line and a clock line. For every single one of these lines, for the one that's communicating about MCP temperature, for the trackpad sensor with the SMC, for all these lines, you have a clock line and a data line. And both of them need to be working in order for you to actually have anything. Now, the way this works is you're going to have just a solid single voltage, a straight voltage with a data line. And the way this works is every single time the chip wants to communicate with something else, it's going to short that to ground and it's going to create a spike. And how these spikes look is going to be interpreted by the chip as what percentage is left in your battery, what temperature the CPU is at. Again, how the chip tells that little spike means that you have 60% power left on your battery, that is beyond me. That is for engineers. All you need to know for most basic practical troubleshooting is to see that there is a data line that exists. So in order for me to show you how that works and what a pull-up resistor is and how it does what it does, I'm going to have to actually show it to you so that you can see it. Because if you can't see it, you're never going to understand it. So I'm going to take the oscilloscope, put it over here, and I'm going to zoom in on an SMC data line. All right, so on one side of this resistor, you're going to see 3.42 volts. So what I'm measuring right now is R5280, which is this. And again, this is just the power supply from the machine. So this is one of the power lines, PP3V42_G3H, G3 hot, which is a 3.42 volt power line. Now, on the other side of this resistor, on the other side, since this is a 2.61 kilo ohm resistor, what happens on this side is not going to affect what's happening on the other side. So let me say that again. What's happening on this side is not going to affect what's happening on the other side. So I can do all sorts of short ground on here without fucking up my main system power rail. So let's see what happens on the other side of that resistor. So I'm going to move my scope over to the other side. And what you see is pulsing. See that? Every time that shorts it to ground, it's creating a pulse. And the duration of that pulse, and also how close to 0 volts that pulse is going to be communication. Now again, don't ask me what that communication means. I have no idea how the SMC tells whether the battery is at 58% or 59% based on those pulses. Good luck decoding any of that nonsense. The important thing to know is that this is what a data line is, and here's how it operates. So a pull-up line is simply going to take it's going to create a line and ensure that on the other side of that line, it's isolated from the rest of the machine, and that you're at a constant 3.42 volts. That signal is not going to change unless something else on that side of the line decides to short it to ground or do anything. So every time the SMC, the battery charger, or the battery want to send a message, it will simply make a little pulse. It'll short that signal to ground. And since you have a resistor that's 2.61 kilo ohms between this data line and the main system power line, it's not like you're shorting a main system power line to ground. So you can have as many of these resistors as you want within reason, and you can create as many of these data lines as you want, and they're all isolated from one another. So again, like this rail is going to be separate from this rail. So the trackpad talking to the SMC is going to be different from the MCP talking to the SMC because they're being done on different resistors and they're going to different tabs on the SMC. So even though they're coming from the same PP3V3, even though the same PP3V3 is creating both of these data lines, on the other side of the data line, what they're talking about is private. Now, let me show you what happens if I do something like, let's say, plug a battery in. You're going to see a lot more communication there. So right now I have the system on, and the system is running, but I don't have a battery plugged into the machine. Now, obviously, if I plug a battery in, there's going to be more for it to talk about. So let's see what you can see now. But this one's much more interesting. When the spike comes up, instead of having just one spike, when you zoom in, you can see it's a bunch of spikes. And if I play with the trigger on my oscilloscope, I may even get it to a point where you can see more of it. So see, that's actual talking. So every single time you see a null over here where the 3-volt line is at 0, that's either the SMC, the battery, or the battery charger chip shorting that 3-volt, 0.4 volts to ground in order to create that pulse. And this is all its own language. So this is its way of communicating. And again, don't ask me what any of that stuff means. That is for Apple engineers to know and for us to just guess. But the point is, this is communication. So one of the things I have on my multimeter here is I have a setting called VTOP, where it tells me what the top voltage is. Now, since this data line is running off of a 3.42 volt rail, I know that the top of that data line should be 3.42 volts. So let's say that my data line is stuck with a VTOP of 2.6 volts, or it's stuck with a VTOP of 2 volts. What that's going to tell me if I'm troubleshooting a circuit is that maybe one of these components is constantly shorting it to ground improperly. So let's say that the top of it is only 1.5 volts or 2.5 volts. I know that it's not working the way it's supposed to. I know that the data line is corrupt, and that something, it may be shorting it to ground. Maybe it's my SMC, maybe it's the board, maybe it's the battery charger or the battery. Whatever it is, something may be shorting it to ground that it's not supposed to be. And knowing how a pull-up resistor works, knowing how a data line works is going to help me with that. So here I see healthy pulsing. It's going all the way up to 3.4 volts. It's going all the way down to 0 whenever it wants to. And you can. This is data. This is data moving. This is what it's supposed to look like. If you see nothing here, then you know that something is wrong. Maybe the SMC is not initiating the first pulse. Maybe the battery charger chip is not talking the way it's supposed to. Maybe the battery charger chip is actually pulling the line down, and that could be a problem. So again, one of the things you can do to troubleshoot this, if you don't have an oscilloscope, is you can take a standard multimeter, and you take your multimeter, which I'm going to put sideways so I can fit it in here. So let's see, I won't have to put, here we go. I can stand it up, and you can see it. I'm going to put my multimeter in diode mode, and I'm going to put a red probe on ground, and then I can put the black probe on one side of the data line, and then I get a number. By the way, a lot of people ask me, why do you use diode mode instead of resistance? It's purely for impatience. So watch what happens when I put the multimeter in a mode to just define resistance. This is fucking agonizing. It's just going to keep counting really slowly. I don't have the patience for that shit. I want an answer in a second. I don't have I'm lucky that my hands are steady enough that I can hold that there for 1 second, much less all that time. Watch diode mode. You get a number. It stays. It sticks. It's there. It's done. It's good. It only moves around if my finger moves. And I have an instant and precise reading. Now, you know, if you measure another board and you get 0.441 and then you measure your board and you get 0.121, then you know that something is wrong with your data line, even if you don't have an oscilloscope to see it. And then you can go about injecting voltage into your data line. You can inject 3.42 volts in there and see what chip gets hot by trying to find the short. Again, I have a video on how to find a short in a board without a $6,000 camera that you should watch if that's of interest to you. But that is pretty much what a data line is. A data line is simply a method between which other components can communicate, and the way that they communicate is with a pull-up resistor. Again, if I take that pull-up resistor away, we're going to be stuck at 0 volts. So the chip is creating communication. The chip is creating communication and using its language by taking that 3.42 volts and shorting it to ground. If I have no power here because I have no pull-up resistor on that data line, if the 3.42 volts is not being brought to that data line is always going to be at 0. Since the chip communicates by turning a higher voltage into 0, if I start with 0, I'm not going to have any communication to begin with, and it's not going to work. So that's the pull-up resistor's place in a circuit.